Okay, so we have minus our speaker takes from Adam Mickiewicz University in Poznań, and he will tell us about the ergodic hierarchy of mixing and all the other things.
Thank you very much for the introduction, and thank you for the opportunity to speak at your seminar. I'm very happy I get to give this talk because I wrote here that this is based on this archive paper, which originally it was, but while I was preparing this talk, I made some new observations, so now I can tell you more than what's in the archive paper. So I'm personally happy about that as well. So my plan is I'm first going to just review some basic facts about the ergodic hierarchy of mixing, which should mostly just be review for everyone, and also just mention the classical versions of van der Corput's difference theorem and where they are used in ergodic theory, just to give some context. And then I'm going to state some of the generalizations of van der Corput's difference theorem that I proved that show a connection to mixing and the ergodic hierarchy. And I'm not going to give any proofs because the proofs are very technical, but I'm hoping that after doing some review of the ergodic hierarchy of mixing, the ideas behind the proofs will be obvious, even if the details may be plentiful. And then at the end, I'll also show how these same ideas can be applied to Katai's orthogonality criteria to give some generalizations there. And of course, if you have any questions during the talk, you can just raise your hand or just tell me to stop if I'm going too fast and ask for a question. I would much rather have you ask questions so that you understand what I'm talking about rather than me just throwing a bunch of math words at you. So let's go ahead and begin with van der Corput's difference theorem and mixing. Van der Corput's difference theorem first appeared in the context of uniform distribution, and a sequence of numbers in the 0-1 interval is uniformly distributed if the sequence appears in any open interval AB with the correct frequency, which just means you look at the indices for which xn is inside of your interval, and if in the limit the proportion of these indices is equal to the length of the interval, then that's the correct frequency, and the sequence is uniformly distributed. And the original van der Corput difference theorem says that if you take some sequence xn in the 0-1 interval, and you know that xn plus h minus xn is uniformly distributed for every h, then you can conclude that the original sequence xn is itself uniformly distributed. And one of the nice applications of this is to show that the sequence n squared alpha is uniformly distributed if alpha is a rational number, because it's really easy to show that just n alpha, so if you get rid of the square, n alpha is uniformly distributed. That's Kroneker's theorem. So if you want to show that n squared alpha is uniformly distributed, you just take the differences. The differences are linear. And okay, maybe you get some 2h alpha or something, but if alphas are rational, then 2h alphas are rational. So you can do a little bit of work and see that n squared alpha satisfies this condition. Therefore, it's uniformly distributed. And then you can use induction and show that the same thing works for higher degree polynomials. N cubed alpha, n to the 4th alpha, or just some degree 5 polynomial times alpha. They're all going to be uniformly distributed. Now, for ergodic theory, sometimes there are connections to uniform distribution, but more commonly we use these variants of van der Corput's theorem in Hilbert spaces. So the first of these variants is the following. We take some Hilbert space H, and now we take a bounded sequence of vectors in the Hilbert space, and we assume that the differences converge to 0 in this sense. So rather than xn plus h minus xn, we're taking an inner product of xn plus h with xn. And then we take the Shazaro average, which is kind of like the counting the frequency that we had in uniform distribution. And if this Shazaro average is equal to 0 for every h, then we conclude that the original sequence has a Shazaro average of 0 in norm. And excuse me, you can see I made this gray because later on there will be other gray things. So hopefully this will illuminate some of the connections, which I'll also say out loud. But I like color coding when I can. And another version of this theorem is that we start in a Hilbert space. We take a bounded sequence of vectors, and now we've somewhat weakened the assumption. So we're still taking these Shazaro averages of inner products of xn plus h with xn, but rather than requiring that each of the Shazaro averages be equal to 0, I'm only requiring that in the limit as h goes to infinity, it approaches 0. So this is a strictly weaker assumption, but we get the same conclusion, that the norm of the Shazaro averages converges to 0. And lastly, third version is that same setup, Hilbert space, and a bounded sequence of vectors xn, but now I further weaken the assumption. So we have these same Shazaro averages as before, the xn plus h with xn. And now, instead of assuming that the limit with respect to h goes to 0, I'm assuming that the average with respect to h approaches 0 in the limit. And this is strictly weaker again. And we still get the same conclusion, that the original sequence of vectors will converge to 0 in norm. Or sorry, the Shazaro average of the original sequence of vectors will converge to 0 in norm. And if you look at this paper by Bergelsen, the weakly mixing polynomial exhaustion technique, which is one of the first occurrences of all three of these theorems, they basically have the same proof. So we may wonder, like, this is the weakest version, or sorry, the version with the weakest assumptions. So are the previous two versions even of any use? Why would you bother checking those? Because they all give you the same conclusion, so we can just use this one all the time and just forget about the first two. And another question is, I just showed you 3 van der Corput difference theorems in Hilbert spaces, but I only showed you 1 van der Corput difference theorem in uniform distribution. So you may wonder, are there other van der Corput difference theorems in the context of uniform distribution? How can you weaken those assumptions? So I will partially answer these questions during the talk, and some of the other answers I'll just have to tell you to look at my thesis if I manage to pique your interest, because obviously I have finite time here. So what are some uses of these van der Corput difference theorems in ergodic theory? Well, this first theorem, Poincare recurrence, does not use van der Corput. It's just an easy consequence of the pigeonhole principle, but it's a good starting point for us. If we take a measure preserving system, which is just a probability space along with a mu measure preserving transformation T, and we take some measurable set of positive measure, then Poincare tells us that there is some integer n such that the set A returns to itself under T, under this definition of returns. It has a non-trivial intersection with itself. One of the generalizations of this theorem is due to Furstenberg and Sarkozy. Sarkozy didn't prove it in the context of measure preserving systems, but he proved something equivalent, which is why I'm attributing this to both of them. And they published their papers in about the same time. I believe actually Furstenberg's paper mentioned Sarkozy's paper, even though the dates. I think Sarkozy's was published afterwards. But the generalization is, again, we start with a measure preserving system, and we take a set with positive measure, and now we can find the integer n such that a will return to itself, but not at time n, at time n squared. So we can refine the return times of a and make it a perfect square. And depending on, you can prove this in a couple different ways, but any of the ways that you prove it will use one form of van der Corput's difference theorem. Another famous result that uses van der Corput's difference theorem is the Furstenberg multiple recurrence theorem, which says that if you take a measure preserving system and a set of positive measure, then for any length L, you can find the integer n such that not only a returns to itself at time n, we have this multiple recurrence, or this multiple intersection. A t to the minus na, t to the minus 2na, all the way up to t to the minus lna, they all intersect each other in a set of positive measure. And this uses something equivalent to the third form of van der Corput's difference theorem. And lastly, we can combine both of these generalizations to get the polynomial sum-ready theorem, or sorry, polynomial multiple recurrence theorem, due to Bergholz and Leibniz. So now we take a probability space and we take L different measure preserving transformations, and we assume that the transformations commute with each other. And then for any measurable set of positive measure and any collection of polynomials that send 0 to 0, you can find an n such that all of these sets intersect each other with positive measure. So A, and then the first transformation to the power of the first polynomial evaluated at n, with the intersected with the second transformation to the power of the second polynomial all the way down to the, sorry, I should have put an L over here. The Lth transformation intersected with the power to the Lth polynomial. And this also uses something equivalent to the third form of van der Corput. So in general, when we're studying multiple recurrence or multiple ergodic averages, van der Corput's difference theorem is useful for reducing the complexity in the powers of the transformation and in reducing the number of terms in the transformation, which is why it's such a heavily used tool. And of course, there are many other results in the literature that use van der Corput's difference theorem, but for now, I just wanted to list these. Okay, so now I have to review some mixing for you so that I can hopefully show you the idea behind the generalizations of van der Corput that are coming up later. So I'm going to denote by this mathcal x the measure preserving system x dut, and we know that one of the we can characterize mixing in terms of the functions in L2 of the measure space. So if we look at all of the functions f and g in L2, and this 0, L2 0 means that the integral is 0. So I'm removing the constant term just to normalize these functions. If the Shazaro average of the inner products of u, t, and f with g converges to 0, then the system is going to be ergodic. If instead of just taking the ordinary Shazaro average, we take the strong Shazaro average, where I've now taken absolute values around the inner product, and it still converges to 0, then the system is weakly mixing. If we take the IP star limit of these inner products and it goes to 0, the system is mildly mixing. And I think IP star convergence and mild mixing may be slightly less popular or well-known than weak mixing and ergodicity, but I'm not going to make too much use of this, so it's not too important if you're not familiar with the notions of IP star. it's just important to know that there is a next level in this hierarchy. And of course, strong mixing is if you just take the ordinary limit of these inner products and it goes to 0. And lastly, maybe this isn't traditionally part of the ergodic hierarchy of mixing, but I just felt like I should put it in here because I didn't want to give it its own slide. If the L20 of x mu has a basis of this form, where you just take some functions fn, and then you take all of their orbits, ut to the n. Oh, I should say orthogonal basis. That's the important part here. Sorry, I mixed up the definition of basis when I was writing this. It's very important that I say it has an orthogonal basis of the form where you just take some functions and take their orbits under the induced operator. Then the system has countable Lebesgue spectrum. And it's worth mentioning that there are systems with 0 entropy that still have countable Lebesgue spectrum. So, as some of you may know, K-mixing is normally what comes after strong mixing in the ergodic hierarchy. And K-mixing implies countable Lebesgue spectrum, but countable Lebesgue spectrum does not imply K-mixing. So it's part of why I don't have K-mixing coming up here. As far as Hilbertian phenomena go, this is as good as it gets, countable Lebesgue spectrum. And then K-mixing and verticality have something to do with multiple intersections, so it's not inherently Hilbertian, where all you can do is take inner products, which is just looking at pairs of intersections at a time. So hopefully most of this is just review, and then next, yeah, and one other thing I might mention a few times later on in the presentation is, rather than saying the system X is ergodic, if this holds for a single F and every possible G, then I can just say that the element F is ergodic, right? Or if this holds for a single F, but for every possible G, then I'll say that F is strongly mixing. So any questions up here? Okay. So now this, which is in most textbooks on ergodic theory, is basically the idea behind my proofs of the generalizations of van der Corput's difference theorem. I gave you the definitions of mixing, ergodicity, weak mixing, mild mixing, and strong mixing with F and G. But now this theorem says that I just have to check that the criteria holds for F and F. And if it holds for F and F, you can conclude that it holds for F and G. Right? You can use some polarization identities to upgrade the F and F situation into the F and G situation. And yeah, if for example, this equation holds for a single F, then I can say that the element F is ergodic using the definition in the previous slide. Or if this holds for a single F, then the element F is strong mixing. So if this holds for a single F, then I can put any G that I want right here. Okay. Now, here I have some of the opposites of mixing. I don't know if these have a proper name. I just decided to call them anti-mixing. I made that up. It's probably not an official term. So, this is the equivalent definition of ergodicity, because one direction is easy, right? If it holds on the previous slide, I assume that this holds for every F and every G, which implies that it holds for every F with itself, because I can take F equals G. The theorem is that if I only check that it holds for F with F, then I can go back and conclude that it holds for F and G. Does that answer your question?
Just a number of multiplications.
Yeah, I just wrote for every F once because I didn't want to put it 4 times. Okay. So the opposites of mixing is how I get applications out of my more general theorems. So what is the opposite of ergodicity? It is invariance. Right? If UT of F equals F, then the element F is invariant. And as we know, one of the ways to prove the mean ergodic theorem is you take your Hilbert space and you split it into the cocycles, which are kind of like ergodic elements, and the invariant subspace. And this is a decomposition, right? Because it's a Hilbert space decomposition, it's showing that invariant elements are opposite to cocycles, are opposite to ergodic elements. And okay, so I wrote something a little technical here. I'm saying that here, if you take a P limit where P is some very special type of ultrafilter, and this P limit of UTNF is equal to F in the weak topology, then F is compact. And this is maybe foreign to you if you haven't seen ultrafilters before. What's probably more familiar to most people is the Kronecker factor, where you take a sub-sigma algebra of the original sigma algebra that makes the measure preserving system isomorphic to a group rotation. And this sigma algebra, or this system, if you will, is usually referred to as the Kronecker factor. And to determine whether or not your function f is coming from this Kronecker factor, or maybe another equivalent version that I didn't write is if f has a pre-compact orbit, it's the same as checking if for some notion of convergence, right? The details here aren't important. What I'm trying to say is for some notion of convergence that is well-defined somewhere, the sequence UTNF converges to F. So it's more general than invariance, because I'm not saying that it's literally equal to itself when you apply the operator, but it is converging to itself in the limit. And this compactness is the opposite of weak mixing. There's the Jacobs, the Louis Glicksberg decomposition of Hilbert space, where you take, or I usually refer to it as the compact weak mixing decomposition. You take the set of vectors that are weakly mixing and the set of vectors that have a pre-compact orbit, and this gives you orthogonal decomposition of your Hilbert space. So again, that's just saying compactnesses or group rotations are the opposite of weak mixing. And then here, rigidity is the opposite of mild mixing. So the function f is rigid if there is some sequence nk such that along this sequence u of t to the power of nk converges to f in norm. And this is more general than what we had here because, behind the scenes, hidden in the definition of this ultrafilter, it's kind of saying that there's a large number of n's for which this is close to this. But over here, I'm just saying there is some sequence nk for which this happens. So maybe the nk could be 2 to the 2 to the 2 to the n. Some extremely sparse sequence. And as long as the sequence exists, then the element f is rigid. And this is the opposite of mild mixing. One of the definitions of mild mixing is that there are no rigid elements in L2 of your measure preserving system. Right? So maybe to make these, I've been vaguely saying that these are the opposites. To make it more precise and concrete, This is one of the things I mean when I say that these notions are opposite to each other. So I take some measure-constrained system, and I take some f and g in L2 of that space, and I want to know when is the inner product of f and g 0? When are these two vectors orthogonal to each other? Well, as I mentioned before, if f is invariant and g is ergodic, then the inner product is 0. Right? That's, again, if you look at the proof of the mean ergodic theorem, this is used in the invariant ergodic decomposition. Similarly, if f is compact and g is weakly mixing, then the inner product is 0. And if f is rigid and g is mildly mixing, then again, the inner product is 0.
Do you assume something about the integrals, like integral 0 in here? Partial integral 0.
Yes. Oh, okay. Yeah, I should have put the 0 over there. That's a good point. Thank you. Yeah, I am going to put these on my website later, so it's good that you point out typos. I can fix them before I upload it. And you know, if you're uncomfortable with what I said here, this theorem is the important part, because basically to get applications to multiple ergodic averages, I'm just going to be viewing a certain sequence, a certain object as invariant and another object as ergodic, and then you take an inner product and you can conclude that some Shizaro average is 0. Or if you view some sequence as a rigid sequence, and you can say that some other sequence is a mildly mixing sequence, then the Shizaro average turns into some kind of inner product, and their inner product is going to be 0. So this is the other half of the ideas that's underlying my applications. Now, so everything I've said up to now, I think is more or less known. This next part, okay, I guess this is also known, but the next theorem that comes after this is maybe not review. I would be happy if someone told me that what's coming up next is actually well known, but you know what, I'm getting ahead of myself. We'll see when we get there. So the Bloom-Hansen theorem says that if we take a measurement-driven system and it is, if we take a measurement-driven system, it is a strongly mixing system if and only if for any f with 0 integral and any increasing sequence of natural numbers, this Shizaro average along the subsequence converges to 0. It's not a particularly difficult theorem to prove, but I think it's quite aesthetic and nice. And one of the consequences of this is the following. So this is what I was alluding to earlier when I said that while I was preparing for this, I made this observation. We can make this definition, and if we use this definition, the results that I'm going to have in my applications are actually more general than what's currently on my archive paper. So what I want to do here with this definition of weakly rigid is I want to give you an opposite of strong mixing, right? Because here, we know the ergodic hierarchy of mixing goes beyond mild mixing, but I didn't give you any opposites of strong mixing are countable to Bake spectrum. And that's because I just assumed that there wasn't any. I haven't seen it in the literature yet, but hopefully I can convince you that this weakly rigid is some sort of opposite to strong mixing. So if there exists some g in L2 and some sequence of integers nk such that our function f is equal to this Shizaro average, then I'll call the function f weakly rigid. You know, because I'm calling it weakly rigid, I'm implying that this is a more general notion than rigid, and we can verify this. If we assume that f was actually rigid, then I could pick these nks so that ut nk of f, right, we'll just put the f here, converges to f by the definition of rigidity, And if I take the Shizaro average of something that converges to F, well, the Shizaro average is also going to converge to F. So any rigid element can be represented in this form by just taking G equals F and by letting the sequence be the sequence along which you're rigid. I would like to say that there are weakly rigid elements that are not rigid, but I haven't formally written anything out and checked all the details, so I guess I'll just leave it as a question for now. I'm convinced that this is a strictly more general notion, but I have yet to rigorously prove it. And of course, what we can show is that if F is weakly rigid and G is strongly mixing, then the inner product is 0. So in this sense, weakly rigid is an opposite to strongly mixing. Now, what I would really like to complete the picture and to truly say that these are opposites to each other is to say something like, if G is not, sorry, let's go here. If the system is not strongly mixing, then every element, or not every element, yeah, then there exists an element which is weakly rigid. And that's actually not obvious from the Bloom-Hinton theorem, because if the system is not strongly mixing, then maybe these limits just don't exist. So that's something to overcome. And I would also like to say that there exists a mildly mixing system where every element is weakly rigid. That would, in my opinion, truly show that weakly rigid is the opposite of strong mixing, if we could show these two things.
I have a question.
Yes.
So if you take all weakly rigid functions, then you have to.
I tried to prove this and I couldn't. That's a good question, and it's related to what I'm asking. So I guess another thing you could show is that, one, show that all of the weakly rigid functions together give you a factor, and then after you prove that, show that a system is strongly mixing if and only if it has no weakly rigid factor. If these were theorems, then I would be pretty happy. I think that would be interesting. But unfortunately, the only thing I can prove so far is this. This is easy to prove once you're comfortable with the Bloom-Hinton theorem. But as far as the factors and all of that go, I have not had any success. And of course, now I can give you an opposite to comfortable debate spectrum as well. So now I'm going to call an element F very weakly rigid. And again, this is a definition I made up. I would be happy if one of you told me this is already in the literature somewhere, so I could learn something about it. But F is very weakly rigid if there is some sequence of functions and some sequence of sequences and a single sequence of integers, such that F is now the Shizaro average of this quantity here. So similar to before, I'm taking a Shizaro average. I'm taking a Shizaro average of ut to the nk, but instead of applying it to a single function g, I'm applying it to gk. So at each step in the limit, I'm permitted to change the function. And I'm also allowing myself some weights, some complex number weights. And my only restrictions on these functions and weights is that their combined size is little o of k squared. So it should be obvious that this is more general than weakly rigid, because weakly rigid means you take the same function g every time, and the complex numbers are just 1, right? And then of course, why did I bother with this complicated definition? Well, if F is very weakly rigid and G is in some subspace of your Hilbert space that has the vague spectrum, then the inner product is going to be 0. So again, you can, this will be somewhat annoying to prove because there's just a lot of symbols to go through, but if you can bear through the symbols, then it's not too complicated. You just use some Cauchy-Schwarz and the fact that you're going to have a lot of orthogonal bases by the fact that you have a vague spectrum. And this is good enough to get some applications, but as I mentioned on the previous slide, what would really be interesting to I don't know, make this more appealing is if we could say that the very weakly rigid functions form a factor. That would be nice. I don't know if they do, but I hope that they do. And then if they do form a factor, I would like to say that your system has countable the vague spectrum if and only if there is no very weakly rigid factor. And then to complete the picture, you could also, it would be nice to show that there exists some strongly mixing system such that every element is very weakly rigid. Now, I'm sorry for throwing so much speculation on these last 2 slides, but everything else from here on out is not speculatory. It'll just be, facts. So thank you for bearing with that. Of course, I guess something worth mentioning. There's a paper by Borgelson, Delunco, Rosenblatt, and Lemanchik, which shows that in the space of all measure-preserving transformations on the 0-1 interval, a typical measure-preserving system, some dense G delta set of measure-preserving systems, are weakly mixing and rigid. So in some sense, this is saying that if you were to randomly pick a measure-preserving system, it will be weakly mixing, but it will not at all be rigid. No part of, it won't be mild mixing because it'll just be rigid, which is the opposite of mild mixing. So of course, if a random or a typical measure-preserving system is rigid, then the class of very weakly rigid systems is at least as large as the class of rigid systems, so it's a large class. Okay. So now I want to state 2 of the generalizations of van der Corput's difference theorem that I proved. And after I state those generalizations, we'll look at some applications to multiple ergodic averages. So we have the same setup as we had before for the second van der Corput. We take a bounded sequence of vectors in Hilbert space, and I'm assuming that when we look at these Shazaro averages of the inner products of xn plus h with xn, the Shazaro averages converge to 0 as h goes to infinity. So in the limit, they converge to 0. And now, if we pretend that this lim sup of the Shazaro average of the inner products is itself an inner product of sequences, which can be made precise, but it's annoying to make it precise. So for now, we just pretend that this is some well-defined inner product. Then I'm saying that the limit of some inner product approaches 0. That was basically the definition of strong mixing, right? And here I'm looking at an element, which is the sequence xn, inner product with its own translates, right? Xn plus h. So it's like my unitary operator is the left shift. I'm just shifting the index, and then I'm taking an inner product with itself. They're all going to 0. So the sequence is strongly mixing, which in some vague sense, or actually not too vague, it just means that if you take any other sequence, then these inner products are also going to converge to 0. right? This is the F with F, and this is the F with the G. Now, the only problem here is that, right, if you pick any other sequence, then these limits need not exist. So if the limits don't exist, then the inner product is not well defined, and if it's not well defined, then you can't do anything. So the technicalities of the proof is passing to subsequences which make everything well defined, and then verifying that regardless of which subsequence you pass to, the same result holds true. And there's a lot of details to check there. But morally speaking, this is the idea, is that the inner products with F go to 0, therefore the inner products with F and G go to 0. And rather than F and G being functions in L2, F and G are sequences of vectors from a Hilbert space. And even though I'm like sweeping all the dirt under the rug about like the subsequences, the applications don't have any complications with subsequences. The applications are just genuine Shazaro average exists and equals this. So hopefully that'll make you feel better about the fact that I'm hiding some details here, which I don't know. If you care about them, then I guess you can look at my papers, but I'll let you decide that yourselves. And another generalization is we take our bounded sequence of vectors, and now this is the first Van der Waals. I'm saying that each of the Shazaro averages is exactly equal to 0. I'm not taking any limits this time. Then excuse me. The sequence xn is what I call nearly orthogonal, and what that means is that what I alluded to earlier, there's some other Hilbert space whose vectors are sequences of vectors from the original Hilbert space, and in this new Hilbert space, when I look at all of these translates of the original sequence, so I just shift the starting point, then these translates create an orthogonal set of vectors. So this is kind of like the countable Lebesgue spectrum. Now, so I've shown you a generalization for strong mixing and a generalization for countable Lebesgue spectrum. I haven't said anything about ergodicity, weak mixing, or mild mixing, but hopefully you're convinced that there do exist such Van der Corpets for these other levels as well. And I wrote about them in my thesis. And I also didn't mention anything about uniform distribution here, but I have four other uniform distribution Van der Corpets in my thesis, which are connected to mixing as well. They use the discrepancy of the sequence as a form of inner product. So if you're curious about that, you can talk to me after the talk as well. But I haven't. I don't have space to talk about uniform distribution and Hilbert spaces and Katai, so I had to cut some of it out. And also, Anusha Sarugyan had a paper many years ago, which also showed connections between Van der Corpet-Stifflin's theorem and mixing. So it's related to what I've been saying, and if you're interested, it's also worth examining. Okay. So this, now we're going to get into the applications. First, I'm going to give you two theorems due to Franciki-Nakis. This first one is only due to Franciki-Nakis. The next one is joint work with Franciki-Nakis and Host. And then my first application is going to be related to this. Oh, and I'm sorry, I thought I put some pauses here. I didn't want to bombard you with a giant block of text, but oh well. I'll try to pace myself. So this theorem of Franciki-Nakis is about the idea is that he's saying something about ergodic averages where the transformations don't commute, which is a new topic in ergodic theory, because normally when you talk about ergodic averages with many transformations, you need some level of commutativity assumptions. You saw in the beginning for the polynomial Samaretti theorem, polynomial multiple recurrence theorem, we assumed that the transformations commute. Later work by Leibniz and others extended these results to when the transformations form a nilpotent group. And then there's some work by Bergelsen and Leibniz which show that if your transformations form a solvable group that is not nilpotent, or not virtually nilpotent, so it's genuinely solvable in some sense, then it's very difficult to say anything about multiple ergodic averages. You can make all sorts of crazy things happen. So it is believed that you generally need some sort of commutativity. Now, what Francis does here is he takes he takes probability space, he takes two transformations, T and S, and he makes no commutativity assumption, right? This is any two transformations, T and S. But instead of commutativity, he assumes that if I only look at the first transformation, then the system has zero entropy. So he is replacing the commutativity assumption with a structural assumption. So now, if we take two bounded functions, then we can get an ergodic theorem. And the other important thing is not just that this first transformation has zero entropy. There's a sequence AN here, which, we don't need to know what the Hardy field function is. Basically, if you have some well-behaved, quickly growing sequence, like sufficiently faster than linear, then that's what he's using here to make it, in some sense, orthogonal to the zero entropy sequence and get an ergodic theorem. I kind of made this slide impromptu, but are there any questions? I hope that it made sense. That's a good question. I don't know. Yeah, I don't remember if Francis mentioned anything in his paper. So, sorry, I can't say more about that. But actually, there's one other important thing I should mention. What Francis did show in his paper is that the zero entropy assumption is tight. Zero entropy assumption is tight. So for any system with positive entropy, you can pick some F and some G to basically make these averages do whatever you want. So he mentions that in detail in his paper. So zero entropy is really as good as it gets. And one of the corollaries of the first part is you can say something about recurrence. If we take a measurable set, then these multiple intersections on average are large. The average of these intersections is mu cubed, which is as good as you can expect it to be, right? Because if we took a purely independent system, took a Bernoulli system, the averages would be mu cubed, and it's saying that, yeah, we still have that in this situation as well. And then, of course, the second theorem, so to state the second theorem, I should just point out here that when I said the sequence AN is quickly growing and not linear, this the fact that the limit of AN over t to the d plus epsilon has to be infinity, while this limit is also infinity, it's basically saying that AN is not a polynomial. In some sense, AN has to be far away from a polynomial, which is kind of surprising because normally you think polynomials are nice and easy to work with, but in this case, they cause some problems, so he has to assume that they're far away. So in his original paper, Francis asked if the same theorem holds when AN is a polynomial sequence, and then later Francis and Post together published new paper which answered this question, and it uses new techniques to show that yes, everything does still work out for polynomials. The only technicality that arises is if you want the limit to be the correct limit, the product of expectations when you have polynomials, then you need to assume total ergodicity on this transformation. Because polynomials have divisibility issues, but other than that, everything does work out for polynomials. Okay, so that was a lot to digest, but now we're ready for my theorem. So yeah, admittedly, on the one hand, I'm a little sad that I proved a version of this theorem before Franz Ekenakis published his paper, but I didn't, his first paper. But I didn't know that it was interesting. And then now that Franz Ekenakis published his paper, which is more general than my theorem, or at least mostly more general than my theorem, I guess this first application loses a lot of value. But the second, third, and fourth applications have not been subsumed by someone else's work. And there are still some mild differences between my theorem and Franz Ekenakis' theorem. So I'm starting with a probability space and two measure-preserving transformations with no commutativity assumptions. So the same setup as Franz Ekenakis so far. Now the part where he's beaten me is that I'm assuming that this system is very weakly rigid, which, as I said earlier, is not the case for a system of countable Lebesgue spectrum. Now, the degree to which this is the opposite of countable Lebesgue spectrum is not known, but this is as soon as your space gets countable Lebesgue spectrum, it will no longer be very weakly rigid. And as I said before, there exist zero entropy systems that have countable Lebesgue spectrum. So zero entropy is more general than very weakly rigid. So that's where I have to confess that Franz Ekenakis has defeated me. And if you look at my archive paper, it's just, I only state things for rigid. So this is my structural assumption, and then no.
Because you're saying there are more zero entropy systems than just very weakly rigid, because you can have countable Lebesgue spectrum.
Yes.
But what about the other narrative? You look something for
I think very weakly rigid should imply zero entropy, but I should also confess I'm actually not too strong. Yeah. I'm not as knowledgeable about entropy as I should be, because it's one of those topics that feels very important, but I always feel like I don't know enough about it. But yeah, I think this should imply zero entropy. Sorry, now that thought is just distracting me. And then I'm also assuming that the other system with S is totally ergodic, although I don't know, maybe I could have worded the theorem better. This totally ergodic assumption is not strictly necessary, and in the three parts of my theorem, the third part gets rid of the assumption. So, you know, this part, the total ergodicity, Franz Ekenakis hasn't necessarily beaten me where we have the same assumptions here. But maybe I just didn't work things as well as I could have. So now, rather than looking at a Hardy field function, you know, rather than looking at some real valued functions whose derivatives satisfy such and such and whose growth rates satisfy such and such, I'm saying take some sequence of integers and assume that this difference sequence, kn plus h minus kn times alpha, is uniformly distributed for all irrational alpha. So this is implied by Hardy field functions that grow sufficiently quickly, or by temperate functions. They will satisfy this condition. So if we have this uniform distribution, and I guess more importantly, I should mention, it's not only satisfied by Hardy field functions and temperate functions, it's satisfied by polynomials, which I wrote on the first slide, right? N squared, or any polynomial of degree 2 or more is going to satisfy this condition for every irrational alpha. Then we can get that these multiple ergodic averages with the non-commuting transformation converge to the expected value. And of course, we can get the application to recurrence as well, that if we take a measurable set A, then the average of these intersections is going to be at least UA cubed. This part II is deduced from part I in the same fashion that Francis did. And then the third part is that if the difference sequence is uniformly distributed in its orbit closure for every alpha, so now I also look at the rational values of alpha, and obviously if alpha is rational, the orbit is going to be a finite set of points, so I can't ask for uniform distribution, but I can ask for uniform distribution within the finite set of points. And if that happens for all alpha, then I don't need any ergodicity assumptions on S. S can just be any system whatsoever. So if I'm not working with a polynomial sequence, but I'm working with a, say like n to the power of floor value of n to the 3 halves, or floor value of n squared log n, or something like this, then S can be anything. So one of the, I guess, notable differences of my results with the previous two results is it's a single proof, but it applies to polynomials and to, I guess, non-polynomials or other functions as well. And I guess I would like to say it's elementary in that it doesn't use anything about nil manifolds, but then it's subjective as to how elementary it is given the work that goes into proving the van der Waals, so that part is debatable. This is the first of my applications. Any questions here? Yeah, sorry. I was writing that everywhere else. I should have written it here as well. It is mod 1. Thank you. Okay. So again, before I state my second application, I need to give you a context by showing you another theorem. And yeah, I don't know what happened to all of my pauses at the second half of this presentation. I apologize again. I really dislike throwing huge walls of text at people, but here I am doing it to you. Okay, so now this is a new theorem due to Francis, Lassine, and Weirdle. And it's trying to basically show that there's some set of integers which is good for recurrence of k-1 transformations, but is not good for the recurrence of k transformations. That's the general idea of this theorem. So to be more precise, we pick an integer k, which is at least 2, and we pick some irrational number alpha. And I can create this set Rk, which is the integers n, such that n to the k times alpha is inside of the interval 1/4 to 3/4. So a very well-defined set. Now, if I take a probability space and any k-1 commuting transformations, commuting a measure preserving transformation, and any set with positive measure, then there is some n in my set R, sorry, that should be Rk, not just R, that makes this multiple intersection have positive measure. However, there is some measure preserving system and a set A with positive measure such that this k-fold multiple intersection, oops, this is supposed, oh no, yeah, okay. This is supposed to be equal to 0. That's a very bad typo. So this set will, it's so good for k-1 recurrence that I don't even need the same transformation. It could just be any transformations that commute. But it's so bad for k recurrence that even when I restrict myself to one transformation and just look at its powers, which in some sense that's maybe the simplest thing to do, is to just look at powers of the same transformation, you will not get recurrence. The intersections will have measure of 0. Okay, so my generalization is, I'm generalizing the second half. I'm starting with the same set. So I'm taking k at least 2, alpha is irrational, rk is the same set as before, nothing has changed so far. I'm taking a probability space and k-1 commuting measure preserving transformations. So all of this is the same setup as before, but now I take another transformation such that the system with just this one transformation is very weakly rigid. And when I look at all of the transformations together, it makes a nilpotent group. So it doesn't even have to, this S does not have to commute with the other transformations. It just has to behave nilpotently with them. Then, for any set with positive measure, there is some n in our set such that this k-fold intersection actually has positive measure. So one way to interpret this is that if we go back, it looks like they're creating a set Rk which distinguishes between k-1 and k recurrence, but for this same set, we can still get k recurrence, even when this doesn't commute with the other transformations. What's really being detected is if one of the k transformations is sufficiently complex. Is I guess it's kind of strange to think of zero entropy as complex, but if it's more complex than very weakly rigid, then that's what makes this break. It's not the fact that I had an extra transformation. Right. And if you want to, sorry, maybe I should have organized this better. But basically, the thing I was about to show is that I want to give you a concrete example of a system for which part 2 holds, for which these multiple intersections are equal to 0 along this set. So if I take k equals 2, I can make a very concrete system. I just work on the 2-dimensional torus with Lebesgue measure, and my transformation is to add alpha, some irrational number in the first coordinate, and in the second coordinate, I do y plus x, so it's a skew product. And this is the example that we can use in item I when k is 2. And this system has 0 entropy. So I cannot relax this assumption from very weakly rigid to 0 entropy. Now, it's worth lingering on this for a while because I already told you that Frantzikakis has beaten my first result because he proved it for 0 entropy, and I only have it for very weakly rigid. And it's natural to wonder, can this van der Corput business be extended to also apply to some 0 entropy situations? Because we know that the results do hold for 0 entropy situations. But No, we do genuinely need new methods because this is I guess, zero entropy situation for which the desired result is not true, right? This cannot be made into a zero entropy S. So this is just showing the limitations of the van der Corput difference theorems, that they can work for very weakly rigid systems, but they cannot work for zero entropy systems in general that will require more techniques or new techniques. Yes. What? Integral?
Why you choose this one? You can change for other.
It just needs to, I think any interval, say, of measure smaller than 1/2 and not containing 0 is probably good enough. You can certainly replace it with other intervals. Like if you were to shrink it to, I don't know, 3/8 up to 5/8, it will still work. But basically, it is okay. So how do we fix it? So this. So okay, I'll try to give some ideas behind the proof, which is maybe says something about why this interval exists. So, are you familiar with the fact that this system can be used to generate n squared alpha in the second coordinate? Okay, good. So there are, if you take bigger skew products, then in the kth coordinate you can generate n to the k alpha. So if you take a big enough skew product, then this is kind of like saying to only look at those points whose kth coordinates are in this interval. So it's kind of like looking at the preimages of some open set in a K torus, and this will not be good for K recurrence because I'm not going to explain it, but I'll keep it vague. The skew products make these n to the k alphas, and this is forcing the n to the k alpha to stay away from 0. But recurrence would mean that n to the k alpha is coming back to 0. And that part needs to be made precise. That's part of the work of their papers to work out the details of that. But because the skew product on a K torus is in some sense independent from skew products on a K-1 torus, even if I force non-recurrence on the K torus, as long as I'm forcing it on the actual K coordinate, which is independent of the first K-1 coordinates, I will still maintain recurrence in the first K-1 coordinates, which happens to also just be good for recurrence in systems with K-1 transformations. Is that satisfactory? Any other questions? Okay. And now for this one, there's no background. I mean, I guess I could have given some background, but I just decided to jump straight into the theorem. So now I'm going to take a probability space. I'm going to take two measures of transformations. There is no commutativity assumptions as usual. That's been the theme so far. The first system I'm going to assume is very weakly rigid. And the second system is totally ergodic. And this time I genuinely need the total ergodicity assumption. There's no getting around it. Now I'm going to take a collection of polynomials. And I have some independence condition, but basically, if you would like, you could think, that the difference in degrees between any two of these polynomials is at least 2. That implies the independence condition. But if you want, we can also just say that some of these differences are linearly independent over the rationals. And so if you take polynomials that are sufficiently independent, then for any k+1 bounded functions, we can get that this multiple ergodic average converges to the expected value. So unlike before, I'm not just taking products of 2 functions. I mean, I guess I was already taking products of k in the previous one as well, but I have a product of k+1 functions, and here the powers are difference polynomials, and the ergodic average converges to what you would expect it to converge to. So this is basically just using a result of Breinekra and I believe Host that showed that if I forget about T, Breinekra and Host showed that these multiple ergodic averages converge to the product of the integrals if you assume total ergodicity and some level of independence on polynomials. And now all I'm saying is if you assume a little bit more independence on polynomials, then you can use van der Corput, and then you can add on an extra term to this ergodic average, which doesn't have to commute with any of the other transformations. It just needs to be structurally of low complexity. And then the last of the applications is we take properly spaced, and now I take 3 transformations, T, S1, and S2. They're all measure preserving, of course. And I make no commutativity assumptions between any of these 3 transformations. Just, yeah. And the first system I'm going to assume is very weakly rigid, so it has low complexity. And the second system I'm assuming is weakly mixing. And the middle system with S1, I make no assumptions at all. That could be any system that you like. Now we take some functions. You can either take a polynomial of degree at least 2, like n squared or n cubed minus n, or maybe if you prefer, you could take a function of this form, n to the alpha times log n to the beta. And now, if we take any 3 bounded functions, such that the third function has 0 integral, then this ergodic average converges to 0, which is the expected value because I assume that the third function has 0 integral. So now the ergodic average is just a Tnf, and then S1 to the n of F1, and then the polynomial or the n to the alpha log n to the beta. It appears here in the exponent of S2. So if I take the product of these 3 terms with no commutativity assumptions, then I can get convergence. And again, I should point out now that I'm at the end of my last application, I did not lie to you, or I did not sweep any details under the rug regarding these applications. The statements are exactly as is. So even though I had to cheat when I told you the statements of my van der Corput theorems, I said there's something happening with subsequences that's kind of complicated, and I don't want to talk to you about the details now. Those details don't make problems when you're going for applications, because in these applications, I just have the ordinary Shizar average. It exists and it equals to something that I know. Okay, so that being said, I'll finish off by talking about how some of these ideas can be applied to Katai's orthogonality criterion. I unfortunately don't really have any applications here, because I guess this was something I've been thinking about more recently, whereas the Vanguard corporate business I've been thinking about for a little bit too long now. But I don't know. Hopefully, if this is of some interest to anyone here working on Sarnak's conjecture, then we can find some application or something. The first, the original Katai's orthogonality criteria says we take some bounded sequence of complex numbers, and we assume that these Shazaro averages, the Shazaro average of C sub Pn times the complex conjugate of C times Qn is equal to 0 for all distinct primes P and Q. And then, if you take any bounded multiplicative function, you can conclude that the correlation is 0. The Shazaro average of Cn times the complex conjugate of Fn is 0. I guess you don't really need this complex conjugate here, but I just wanted it to look the same, so I put it there. And as we know, this is very useful because these days Sarnak's conjecture is a hot topic, and we want to know, we can take f to be the Mobius function, because the Mobius function is a multiplicative function, and we want to know what sequences Cn we can put here to make the Shazaro average of the Mobius function equal to 0. And Katai's orthogonality criteria helps us find many such sequences, such as e to the 2 pi I alpha. This was shown by number theorists. I mean, maybe I should actually write this. It's not on my slides. So this is a result that's very easy to prove using Katai's criteria, because mu is multiplicative and e to the 2 pi I and alpha certainly satisfies this condition. So then you can get this result very quickly. Now, of course, the number theorists have proved this a long time ago, and in some sense, they've proved the better version because they have a control on the rate of decay of the limit. It is significantly more work to do it. And then, of course, with Katai's criteria, it's very easy to replace this n with, say, n squared or n cubed. Right. I can also do so you take a non-constant polynomial, P of n, then you can conclude that the Shazaro average of e to the 2 pi I P of n with mu is also equal to 0, because the polynomial is also going to satisfy Katai's criteria. So how can we get some generalizations of this? Now, sorry, before I go on, I'll show you 3 generalizations, but I guess maybe the first has the most potential to be used, because I would think that the most common usage of this is to show that something is orthogonal to the Mobius function or to some other multiplicative function that's of interest to number theorists. So when I generalize this theorem, what I would think is the most useful generalization is to weaken the assumptions while maintaining the conclusion that it works for any bounded multiplicative f. So that's what my first generalization does. But the second and third generalization will still have a weaker assumption than what we see here, but a stronger assumption than the first, and they'll instead be focused on generalizing the function f. So this is this first theorem is a version of Katai's criteria that corresponds to ergodicity. Let's take take the increasing enumeration of the prime numbers, and we take a bounded sequence of complex numbers. This W should not be here. I was editing these slides and I forgot to remove this. We take a bounded sequence of complex numbers such that this average is equal to 0. Now, first of all, we see in the middle, we have the 1 over n sum of c to sub a prime number times n times c sub some other prime number times n. So in the original Katai's criteria, we just assumed that each of these individually averaged out to 0. Now, I'm saying that the average of these averages, right? Because now I'm averaging over all of the different combinations of primes. The average of the averages goes to 0. Whoops, I'm sorry. There we go. So if the average of the averages goes to 0, then that is certainly a weaker assumption than just saying that each of these goes to 0. And I have to, contrary to what we saw before with the van der Corput theorems, on doing an average with pairs over k squared rather than just k, because in some sense we're working with the multiplicative semigroup of integers rather than the additive semigroup of integers. So I can't just cancel out the second prime and move it over to the first side. So that's why I have more terms. Is we're working in a multiplicative situation rather than an additive situation, and things are harder to cancel out. So with this weaker assumption, we can get the same conclusion. If you take a bounded multiplicative function, then these Shazara averages will be 0. And the reason I put multiplicative in purple is that in the setting in which I view these this as some ergodicity condition and the sequence C as some ergodic sequence, you can view multiplicative functions as some sort of invariant function, or some sort of almost invariant function. So this is just to illustrate that the ideas I'm using to prove this are ergodic theory ideas related to ergodicity and invariance. Now, you could also state something for weak mixing and mild mixing, but I don't know, these already feel a little technical, so I thought I would just skip the weak and mild mixing and go to strong mixing. Now, I take some sequence of integers ak. It could be the prime numbers, but it doesn't have to be. It could just be any sequence of natural numbers. And we take a bounded sequence of complex numbers such that for all w, we have that this limit goes to 0. So again, the first lim sup, this Shazara average is kind of like an inner product. And then I'm taking a limit of inner products and assuming that it's equal to 0. So that's a strong mixing kind of phenomenon. But again, the reason it's slightly different than the strong mixing from before, right? I have to assume that from every w this limit goes to 0 is because we're in a multiplicative situation. So I can't just move the AK to the other side or move the AW to the other side. I have to keep these separate, and that's why it looks slightly different than the strong mixing van der Corput. But it is still related to strong mixing. Now, we can work with something more general than multiplicative functions. I guess it would be nicer if I had some examples of functions that satisfy this criteria. I unfortunately don't. This is just some abstract criteria. But basically, what's happening here is I told you that a strong mixing is orthogonal to weakly rigid functions, right? If I take something strong mixing and I take something weakly rigid and I take the inner product, it's going to be 0. So this is just all of this complicated equation is just to say that some function is weakly rigid. Because I said multiplicative functions are compared to invariant functions. So now if I go to weakly rigid functions, it's much more general than invariant functions, which is much more general than multiplicative functions. So here I have a function g, and this is just some other function g that's you can pick after f is c. And I want to approximate f by some sort of combination of translates of this function. So if f was genuinely a multiplicative function, then I could just let dk be g of ak, and then this would cancel out with this, and then you would just get 0. So that's how multiplicative functions fit into this definition. You just make it cancel and everything is 0. And if you take some averages of 0, you just get 0. But I'm saying here, f itself doesn't really need to be multiplicative at all. It just needs to be approximated by, I guess, multiplicative combinations of functions. Yeah. Again, I wish I had some concrete examples, but I don't know. Hopefully, if I show people, then it'll connect to something. But oh, sorry, yeah. And the conclusion is that if f satisfies this conclusion, then the Shazar average is 0. And then we can do the same thing for countable to bake spectrum. So now we have the assumption from Katai's criteria. But again, I'm just using any sequence of integers, not necessarily primes. It was not obvious to me if Katai's proof can also extend to any sequence of integers AK, because he does cite some results and estimates from number theory that concern something with prime numbers. But after he cites these estimates, the rest of his proof can just work for any sequence of integers. So I don't actually know how novel or trivial this part of the generalization is, but that could be something worth examining. So I take any sequence of integers and I take a bounded sequence such that all of these Shazar averages are exactly equal to 0. And now this is the analog of very weakly rigid. So now the function g from before, I can change the function at each step of the limit. I can also change the coefficients of the combination at each step of the limit. And this is already really complicated. So rather than saying the exact relationship between d and g, they just have to satisfy some boundedness relation similar to what I showed you earlier, which I swept under the rug with this air quotes of a very weakly rigid pair. But we can still get the Shazar averages to be 0 in this situation as well. So that is the last of what I had prepared. Thank you for your attention, and if there are any questions, then please ask.
I have a question.
Yes.
So if you compare the proof of these versions of the Katai criteria to the original proof, so where is the main difference? Is the main difference in deciding? I mean, the main difference lies in deciding how to formulate this, and then the proof more or less goes, or?
So For one thing, don't use any number theoretic estimates. So that is one difference. And then I do think that, so if you look at Katai's proof, he actually does say something that more or less says if you have this type of assumption for some subset of primes, if A, W, and AK are some of the prime numbers, and this happens, then you can conclude that the Shazar average is still 0 for any multiplicative function. So for that part, yeah, he already has that, and I tried briefly to see if I could imitate his proof with this assumption and get the same conclusion, and I couldn't do it. But admittedly, I only tried for, I don't know, 30 or 40 minutes, which in the mathematical landscape is not that long. So maybe you could modify his proof to work with this assumption, and I just had to try a little bit harder, but it wasn't immediately obvious to me. And as far as the conclusions go, I think you can modify his proof to work for this conclusion. If F is weakly rigid, then you can make the Shazar average equal to 0. Again, restricting yourself to the prime numbers rather than general AK, because I'm not knowledgeable about generalizing those number theoretic estimates. So you could probably get this theorem on this slide from Katai's work without thinking about strong mixing or rigidity. If someone just showed you this and read Katai's paper, then you can probably prove this one. For weakly rigid, I think you would need to make significant adjustments to this proof. Yes. So I'm taking So as I mentioned before, if we take a sequence of elements in a sequence of vectors in some Hilbert space, I can make a new Hilbert space in which the sequence of vectors is just an element. It is a vector in itself. And then I can make this a shift map on the Hilbert space. And of course, part of the reason I keep mentioning Hilbert spaces is the complex numbers are a Hilbert space. So anything you prove for Hilbert spaces in particular also applies for complex numbers, which is where a lot of the applications we care about are from. And the way that the shift acts on a sequence is just shift it by 1. So it's the dynamics of a unitary operator on a space. And this is unitary because it looks at first like you forget the first coordinate, so you're losing information, so you can't make it inverse. But if you want to do the inverse of this shift, you can just add an arbitrary vector for the first element of the sequence, because the norm or the inner product on this Hilbert space is a Shazaro average, and the Shazaro average can't detect the perspective. So this should graph these invertible, even though I only indexed it by the natural numbers. And if you felt like it, you could do everything indexing it with the C rather than N. It's a trivial distinction. But yes, it's dynamics of a unitary operator on Hilbert space.
And the Hilbert spaces are if they are separable for you, or you use these or not, the variant of the base is important or not?
I have only been working with separable Hilbert spaces because if you, I'm tempted to say that they have to be separable. I'm not certain, but basically, I look at the sequences that I care about. Like, let's say I want to prove that this Cesaro average is equal to 0, but I don't yet know that it's 0. So I look at the sequence Cn, and I look at the sequence Fn. And then I need to create a Hilbert space in which both of these sequences are vectors. So I look at I basically look at the smallest possible Hilbert space in which the two sequences can be viewed as vectors, and that happens to be a separable Hilbert space. And I currently have no reason to look at a bigger Hilbert space, which would end up being non-separable. Yeah.